Hey guys, today we're going to be talking about something new called limits. So the limit is going to be the y value on a graph that the y value that the graph is approaching as x approaches a given number. So instead of it just being the actual y value, so like on here, and it may sometimes be the y value, but instead of it actually being that y value at that point, you're looking at where the graph is approaching. So like if I'm approaching from the left-hand side, then it's coming right here. And if I'm approaching from the right-hand side, it's coming right here. On this one, since there's actually a point there at 2, 4, and that's where the graph is approaching, then the limit as x approaches 2 is just going to be 4. So like if the graph doesn't have a hole in it and it just has a point there, then that's the point you're going to use. But if the graph did have a hole in it, so like if this was an open circle and the point 2, 4 was not actually on the graph, the limit would still be 4 because that's where the graph is approaching from the left and the right. So then here's another example of this looking at a different graph. So this one isn't going to be the same as the last one because there are holes on the graph instead of there actually being like separate points. So for one, we're looking at the behavior around x equals 1 or as x approaches 1. So this first one where it says the limit as x approaches 1 with the minus sign, that's going to be as x approaches 1 from the left. The second one, at limit as x approaches 1 with the plus sign, that's as x approaches 1 from the right. And then if the left and the right are the same, if the limit is the same for the left and the right, then the limit as x approaches 1 is going to be whatever they both are. If it's different, then you're going to say that the limit does not exist. So first on this graph, I just want to start with what f of 1 actually is. And so that's where we have this closed circle right here. That's where if you plug a 1 into this function, then you're going to get 3 for y. But then if you're approaching 1 from the left, then that means we're coming up right here. And it leads us to this open circle. And so if we're approaching 1 from the left, then we're approaching where y equals 2. So the limit as x approaches 1 from the left is going to be 2. So then do the same thing on the other side as x approaches 1 from the right. So we're coming up here like this. And then it leads us to this open circle. So as x approaches 1 from the right, y is at 4. So then since these two don't match up, since it approaches 2 from the left and 4 from the right, and they don't meet up at the same point, then that means the limit as x approaches 1 does not exist. And then the way that you can write that is just write D in E, and that stands for does not exist. So then here's a couple more examples of this. I want you to try to do the graph on the left on your own and then come back and see how I do it. And then the graph on the right is going to be a little bit different, so we're going to talk about that as well. So this graph on the left, as x approaches 0 from the left, it's coming up here and y is at -1. As x approaches 0 from the right, it's coming up to here and y is at 0. So then the limit as x approaches 0, since from the left and right are not the same, does not exist. And then on this other one, as x approaches 0 from the left, our limit is actually going up. This is a vertical asymptote, and it's going all the way up to where y is infinity. So the limit as x approaches 0 from the left is positive infinity. As x approaches 0 from the right, it's also positive infinity. So there's two different ways that you can go about saying what the limit is as x approaches 0. You may see it written as the limit is positive infinity because they're both positive infinity. However, since there's not a value that it's actually approaching, since there's not like an actual real number that it's approaching, you may also see that written as the limit does not exist whenever it's approaching infinity. So If you're writing it out, then either answer would be accepted as correct. If this is written out on multiple choice, then you could see either one, and both of them would be right. So then we need to move on from evaluating by looking at the graph to actually evaluating by hand. So there's going to be a couple of different methods of doing that. The first is just direct substitution. So that means that you're given some function and you're given the x that we're approaching, and you're just going to plug that number in, substitute it in for x, and see if you get an answer. If you get an answer on the first try, that means that's your limit. So on this first example, we're just going to plug in a 2 for x. So it would be 3 times 2 minus 2. And then that's just going to equal 6 minus 2, which is 4. So that's going to be our limit on that first one. We would say the limit as x approaches 2 for 3x minus 2 is 4, and that's it. On the next example, the x is approaching -1, so I'm going to do -1 squared plus -1 plus 6, and so -1 squared is just going to be 1, and then -1 plus 6, and so that's all together just going to equal 6, and so our limit as x approaches -1 is going to be 6. So then this is the second method of evaluating limits by hand. In this case, that means that direct substitution doesn't work. So like, for example, in this first equation here, we have that x is approaching -3. Well, if you plug in -3 in here, then that denominator is going to be 0. So that's why direct substitution is not going to work. There may be a whole or a vertical asymptote at the number that you're looking at like where x is. So in that case, the next thing you're going to try is called the dividing out technique, which is really just simplifying your equation. So we're going to factor that numerator. So x squared plus x minus 6, that's going to factor to x plus 3 times x minus 2. So let's write that in. And then we're still dividing by x plus 3. But then at that point, we have the same factor in the numerator and the denominator, so we can cancel those out. And my simplified version of the equation is just x minus 2. So then what you do is you take the x that you're approaching and you just substitute it into the simplified version of the equation. So we would do -3 minus 2. And then that's going to equal -5. So that's really similar to like when you're finding holes, like we were doing whenever we were in the last unit. But in this case, you're just looking for the limit. So what you would say is the limit as x approaches -3 is -5. So in other words, there's a hole at -3, -5. So it's really similar to whenever we were looking at that. So then on this next example over here, we have x cubed minus x in the numerator, so we can factor out an x, and we would be left with x squared minus 1, and then that's divided by x minus 1. So x squared minus 1, that's a difference of perfect squares, so that can be factored down further. So you can have x times x plus 1 times x minus 1. And that's all divided by x minus 1. So now we're going to cancel out our common factors, which is the x minus 1. And our simplified version of this equation is just x times x plus 1. So then the number that we're looking at is a positive 1. So we're going to plug that into our simplified equation. So 1 times 1 plus 1 is 1 times 2, which is just going to give us 2. So that means that the limit as x approaches 1 for x cubed minus x over x minus 1 is just going to be 2. Okay, so here's just a few different examples. So it may be a good idea to pause here and just see if you can get them on your own, and then unpause and we'll go through them together. So the first one that we're going to do is the limit as x approaches 2 for 3x squared plus 7x minus 1. So in this one, it's not like a rational equation where there's a denominator that zeroes out, so we can just plug in a 2 here. So we would have 3 times 2 squared plus 7 times 2 minus 1. And then you would just evaluate all of that out. So you'd have 2 squared is 4 times 3 is 12 plus 7 times 2, which is 14. So 12 plus 14 is 26. And then minus 1 is going to give us 25. So for the first one, the limit as x approaches 2 is going to be 25. On the second one, it is a rational equation, but pay special attention to what x you're approaching. So we're approaching a positive 3, and if we put a positive 3 in the denominator, that's going to give us a 6 instead of a 0. So just pay attention to that so that you don't add work for yourself that you don't need to add. So on this one, we're plugging in a positive 3. So we would have 3 squared plus 5 times 3 plus 6 in the numerator, and then in the denominator, we would have 3 plus 3. So our denominator is going to equal 6, our numerator is going to equal 3 squared, which is 9, plus 5 times 3, which is 15, plus 6, and all of that added together is going to equal 30. So then our limit is going to be at 30 divided by 6, which is just going to be 5. So then our other two over here are where we're going to have to use that dividing out method, because in this example where x is approaching 1, if we put that in the denominator, that's going to zero it out. So that means we're going to have to factor this numerator. So the way that that's going to factor out is we're going to have an x minus 1 times a 2x plus 3. And that's going to be divided by that x minus 1. So then the factor that's going to cancel is going to be that x minus 1, and we're left with just 2x plus 3. So now we're going to take this 1 and plug it into that. So 2 times 1 plus 3 is just going to give us 5 again. And our last one down here, again, if you plug in -2 in the denominator, that's going to zero that out. So we need to factor our numerator. This numerator is going to factor down to 5x minus 2 times x plus 2. And if you need some extra help with factoring, let me know about that as well. And then we're going to divide by x plus 2. So our common factors are going to cancel, and we're left with 5x minus 2. And then we just need to plug that -2 in there. So 5 times -2 minus 2, and that's going to equal -10 minus 2, which is -12. So look over all of those and check and make sure you got them right. And then there's one more thing with limits that I want to show you today. Okay, so the last scenario on here is there's a case where the dividing out method isn't going to work. So remember that the dividing out method was happening whenever we had holes in our graph. Well, sometimes we don't have holes in our graph, and instead we have a vertical asymptote, like on this graph here. So this is the graph of x plus 6 over x plus 1, which is what we have in all of our problems here. So if we're looking at this, then the limit as x approaches -1 from the left is going to be -infinity. Or you could also say does not exist because it goes off to an infinity. The limit as x approaches -1 from the right is going to be a positive infinity. Or again, you could also say it does not exist because it goes off to infinity. So then the limit as x approaches -1, being that they both go off to infinities and being that they don't go off to the same, it's not a positive infinity or a negative infinity, the only thing you can really say for that is that the limit does not exist. So that happens anytime that you have a vertical asymptote. Whenever you're given that scenario, you're going to always end up saying that the limit does not exist. So hopefully the knowledge that you guys have on rational functions from the last unit will make this type of problem a little bit easier, because you should be able to look at that and know that there's going to be a vertical asymptote at x equals -1. So you would automatically know that in that scenario, the limit is not going to exist. So that is all for limits today. We're going to do a little bit more with them next week as well. But For now, that is all we have for limits.